The broadcast is now starting. All attendees are in listen-only mode.
Good morning and good afternoon. This is Mark Kovich. I'm a System Sales Specialist for IBM. I am part of the IBM Internet of Things Continuous Engineering Organization, now called Connected Products. Thank you for joining our webinar today on Top 10 Tips for Systems Engineering and also Modeling. Today, presenting is Dr. Bruce Douglas. He is the Chief Evangelist at IBM. I'd like to mention that you are in listen mode only and that this webinar is being recorded. We will have a question and answer session at the end of Bruce's presentation. I'd like to point out the question box in your control panel. There's a plus sign there. Just click on that. It'll expand. You can actually take that portion of the control panel and drag it across your desktop and expand it even further if you'd like. And you can submit questions directly to me, and then I'll go ahead and ask the questions to Bruce at the end of his presentation. Also, I'd like to mention that our new archive site is up and running, and I will be copying and pasting that in the chat window for you. So feel free to look for that. And also, if you have difficulty accessing the website, just reply to my automated email that I sent to all registrants of this webinar, and I'll be happy to either send you the presentation or actually send you the .wmv file recording so that you can have it for your own personal reference. And one final note, as far as the presentation, it is available currently. You may download it in the handout section of the control panel. Just click on that little plus sign and you can download it immediately in .pdf. So with that said, I'm going to pass it off to Bruce for the presentation, and feel free to ask any questions. I'll keep them in chronological order, and then we'll ask them at the end of the presentation. So take it away, Bruce.
Well, thanks, Mark, and welcome everyone to this talk about top 10 hints. So in my role as Chief Evangelist and Global Technology Ambassador for IBM, as well as similar roles I've held in other companies, I've been doing modeling for a long, long time. I'm doing system engineering and embedded software development for over 35 years. I've had a number of different roles at different companies doing that, from lead architect to tester to program manager to team lead to process guru to a variety of different roles. And I've seen projects fail and I've seen them succeed. So over the years, I've developed this kind of list of some things that I've discovered that are good things, particularly if you're relatively new to modeling, to kind of listen to and then try to incorporate your own practice. And we're going to go through some of those here today. So going from the kind of least important to the most important, I guess. One of the things I see, and I think that this is a problem for a lot of people, is how do we put things on diagrams? Because you're doing modeling, doing system engineering, you're drawing pictures with semantic meaning, you're modeling. It's not just drawing pictures, right? It's modeling, which you expose in a visual way in some sense or another. How do you take a complex system and divide up those elements onto these pictures, onto these views? So one guidance, been around for quite a while, since the 80s actually, is that you should put 7 elements on a diagram plus or minus 2. If you have 10 elements, you should have at least 2 diagrams, right? This is a really terrible idea. It's a terrible organizational principle for organizing your views of your models. So this rule is that all diagrams should contain 7 elements plus or minus 2, based on a 1956 study called the magic number 7, in which we looked at the ability of humans to remember information. If you give them a list, have them look at it, and you take it away and ask them to recall what's on it. What does this have to do, you might ask, with how many things you put on the diagram? The answer is, well, really nothing, right? Because when you have a diagram, you don't have to rely on short-term memory to recall the elements. They're in front of you. Okay? So that whole idea is just misplaced. It's a bad application of what's called neurolinguistics. Right? But we still need to answer the question, how do I organize my views to have maximum value in my diagrams and my various kinds of viewpoints, whether they're tables or diagrams or textual kind of viewpoints. So what we recommend instead is what we call a diagram mission statement. That every diagram, every view you create is trying to answer a specific question, which we call the mission of the diagram. And it should be answer a question, support some particular line of reasoning, so it should have some specific goal. And you put all the elements necessary to support that mission on the diagram and no other elements. One of the big failings I see when people draw diagrams is they have no really coherent thought as to why these things hang together, or more commonly, they will have 5 or 6 different ideas to try to show in one diagram. It is better to have 5 or 6 different diagrams, each of which has a singular concept, than it is trying to have too many concepts, because then you really can't see anything because there's too much stuff unrelated to the question you're trying to answer. So for example, for a design I did for Star Trek Transporter in one of my books, this diagram here was really to talk about the inertial reference frames in the system and how you coordinate between your spacecraft in 6 degrees of freedom and the transport target in 6 degrees of freedom. And we call that the reference frame management, right? So the whole idea of these structural elements is these are the elements that play a role in that collaboration. And there's more than 7 on there. In fact, there's a bunch. If you look just at the boxes, there are more than 7. But there are also relationships. Within the boxes, we show some of the elements that are related to this particular thing. They may have other elements unrelated to this question, but related to other questions, so they show up on other diagrams. And the model underneath takes care of all of it. And we explicitly state the mission on the diagram. So there are some common missions for class or block if you're doing system engineering block diagrams. So, you know, the packages are your fundamental notational method or excuse me, organizational method in UML and SysML. So what's the contents of a package? How do I organize the interfaces between engineering disciplines like mechanical, electronics, and software, optical, and so on? Generalization taxonomy is a type of kinds of relationships. Software interfaces, system interfaces, structure of individual elements that are maybe complex, collaboration structure, organization of the overall model, snapshots of some instance of time of a running system. You can also look at different kind of architectural viewpoints. The harmony process has 5 key viewpoints: subsystem component view, dependability, which includes safety, reliability, and security, concurrency, resource management view, deployment, which is the allocation of responsibility to different engineering disciplines and how they collaborate, so software, electronics, mechanical. Distribution, how to distribute systems across multiple locations, compute cycles, compute points, and organize them and collect them together to collaborate. And within those, we also have kind of more specific questions we can address, such as, you know, specifically the safety or reliability. What is my tasking model? How do I avoid deadlocks? What kind of design patterns am I using to avoid deadlocks in my concurrency model? What about performance modeling? How do I represent that? How do I manage that? How do I allocate responsibilities to different engineering disciplines? How do I manage protocols for communication? All of those are very important questions you might want to answer, and you can create specific views to address those questions. Number 9, all models are abstractions, and some are useful. I think it's important to note that all human cognition is modeling. And a model is something very specific, that we take a thing and we abstract away properties of things that we're interested in, and we avoid properties that we're not interested in. So if I want to understand how a car engine works, I might look at the structural elements and how gasoline and air flows through it, and how I power the spark plugs, the ignition system. But I don't maybe care what color it is, because that's not it's a characteristic of the actual engine, but it's not a characteristic I perhaps care about in the context of trying to understand how my engine produces torque and force. So whenever we think about something, we always model. We focus on details relevant to the questions we're trying to ask, and we don't focus on those things which are not relevant to those questions. So if we think about something like a chair, if we look at every possible aspect of a chair, we don't have a model of a chair, we have a copy of a chair, right? When we model it, we are subsetting those characteristics, right? So from an engineering standpoint, we might care about stability and structural strength, mechanical control of movement of the chair, raising and lowering the seat, and so on. In manufacturing, we care about things like parts list and materials and assembly flow, how do we construct it. Quality assurance, we care about compliance and standards, materials, tests, and office designer, we care about color, style, and feng shui, right? So those are things we care about. Same chair, different models, depending on what questions I am trying to address. So models always lead details so we can focus on relevant properties. And models succeed to the extent that they allow us to reason better about the world. That's why we model. That's why we use these as our means for cognition. So in terms of systems models and software models, some of the models we create focus on different aspects of the system, but they're all related. So I think it's kind of like, as system engineers, we create a lot of different work products. And we have to demonstrate the connectedness of these models, where we focus on a certain aspect, but it's related to other models. So for example, we talk about requirements models, what we call the functional model. So we build up these computable executable use cases, functional quality service requirements, and we also might do parametric models, things like power models, stability, heat, weight, and other kinds of parametric characteristics. We might want to reason about, is our system safe enough? Is it reliable enough? Is it secure enough? And we use different viewpoints like fault tree analysis, fault means and effect analysis, fault means affecting criticality analysis, asset diagrams, and security analysis diagrams for security. And we call that the dependability model. Then we have control models for control algorithms and mathematical models. And all of these kind of lead into constructing an architectural model consisting of subsystems and interfaces, allocations to subsystems, and use case level subsystems and user stories and requirements that allocate to that place, and so on. Along building this architectural model, we build trade study models to evaluate the effectiveness of different kinds of technical solutions. So would we use a gasoline engine, or should we use an electric engine for this system? What are the pros and cons? What, things like the cost versus the weight versus the torque versus the power output versus the reliability and maintainability. We look at the sum of all those characteristics and do that in trade study models. Once we've done that, we incorporate those trade study models into our architecture. We can then talk about pushing that down to a model-based handoff to the subsystem models. And subsystem models there, then, if you will, allocated to models specific to different engineering disciplines. In this case, we've shown software, electronic, and mechanical. All of these are models, and all of these are related and connected. So speaking of models, there are some people who think that do what's called lightweight modeling, right? What I call napkin models. Sketch out an idea, call it good, and then go do the real work somewhere else, right? I think that's a particularly terrible idea, based on my experience. So napkin models, I think, are a good way to start a conversation. I think they really are. That I got this idea, let's explore that. It's not very well detailed at this point, but we can explore it and solidify up various details to allow us to think about this why we model. So napkin models are a great place, perhaps, to start a conversation. So, for example, when we want to get value out of a model, there are really three properties to give us value: precision, accuracy, and completeness, with respect to the questions we're trying to ask. Again, focusing on the aspects we're really trying to address in our model. And just sketching out some rough idea has really some sort of minimal value at the start. But once we refine that model to something which is precise, accurate, and complete, now we can actually use it to really understand properties of the system, to do a really good design, to make sure we've met all the requirements, to make sure we've met the customer needs, to make sure it's safe and reliable and secure. So for example, take this hand sketch diagram. We've got a student who enrolls in seminars, there's perhaps a waiting list, you've got professors, you've got enrollments. And so what is the purpose? What exactly are you trying to show here? What is are these all the elements related to this question? What is the question you're trying to answer? For the student, are these all the attributes? And what are their types and subranges? For example, phone number. Do I need to have international calling codes as well as a regular phone number? For these operators, so determine eligibility, provide a list of seminars taken, calculate the average mark. So what are the inputs and outputs of these? What are the algorithms? How do these work? How do I determine, for example, am I eligible to take this seminar? What information do I need to answer that question? This doesn't address it. It raises the question, which is the value, but ultimately we have to resolve the question, and that's why we need to add it into the model. So we've got this enrollment relationship. Who decides we can enroll? Who maintains and creates that link? Right? Who decides who can add and drop students? Are there some sort of initial default values for these properties? Who creates and destroys the instances? Right? What happens if the seminar is full? What if it's empty? How can you tell? Do I need to have them for a given seminar, the maximum number of attributes, the maximum number of students rather as an attribute? How do I determine it can be full if I don't have that value? So this is a good way perhaps to start that conversation, but it's not a good place to end that conversation. Okay? So models really need to make precise, as we'll talk about later, verifiable statements, right? And so we can use more formal languages. One of the problems, one of the values of modeling, is that we can use more formal languages. English is a great language. I like English. I speak it reasonably well, I like to think. And it's wonderfully expressive. It's a great language for writing poetry, for writing book reports, for writing books, for expressing yourself. It's a great language for that. It's not good for precision. So if I want to write a poem, English is perhaps a good language for it. It's really pretty hard to write a good state machine using state machine, write a good poem using state machines. It's pretty hard to do that. I did give my wife a very nice poem for Valentine's Day with a state machine. She appreciated it. She's a kind of a nerd, so she appreciated it. But it's not a natural language in which you would write poetry. But it is a good language to describe structure, behavior, functionality, and various kinds of constraints and systems. So we use formal language and semi-formal language to do that. And once we do that, we can now talk about, is this a good statement? Is it correct? And there are ways in which we can verify that. And there are three primary ways. We can look at it, we can inspect it, and we'll talk about that a little bit later. We can test it, which means it has to be a particular subtype of a computable model called an executable model. Or we can analyze it mathematically. Right? We usually do things like theorem proving, reachability analysis. Okay? But the value models really bring is being precise and complete and correct, and being able to verify that. So requirements models allow us to identify defects early. Defects tend to be very, very expensive. And one of the reasons why we care so much about getting requirements correct is if we look at this graph, these numbers actually come from an aerospace company I did some work with, that if they caught a defect in the requirements during or while they're still kind of working on requirements, the cost is about $30 to fix the requirements defect. Okay? If they found it during integration or system testing, it was about $10,000 for them to fix it. If it escaped to the customer, then it was $1 million plus to fix it. Okay? So the cost of finding the defect is pretty high later on in the process. And there are two primary reasons for this. One is there's a cost in just finding the defect in this morass of this large-scale system. You might have an automobile, an aircraft. You've got tens to hundreds of thousands of requirements, millions of requirements. You've got system architecture. You've got all kinds of mechanical pieces and mechanical design, electronic design, software design, architectures. All this stuff is interacting in the system, and now you've discovered it doesn't do what you want. It takes time and effort to find and localize that defect. But even more than that, you now have to throw stuff away and redo it. And even that's not the big cost. It's generation of all the downstream work products necessary that come from that. So if I define, for example, a requirements defect, I now have to redo parts of my architecture and my design and my test cases, and my test plans, and my test procedures because of that requirements defect. So all of that rework is expensive. So if we can find a way to avoid those defects, we can save a lot of money and a lot of time. So we can do that by building requirements models. So this is, of course, a use case diagram where use cases are clusters of coherent requirements representing some sort of usage of the system. So this is for automobile braking system, an ABS auto anti-lock braking system. And we see that we've got ABS braking, we've got normal braking, configure braking, and so on. Each one of these represents a coherent set of anywhere from typically 25 to 100 requirements, something like that, around this usage of the system. And then we can look and say, well, what are the pieces involved? And so this is how a block, use case, system level block representing the use case, with connection points to various actors, elements in the environment with which it interacts. We've got the wheels, and we've got the braking system, and we've got the drivers, right? And so now we can actually formally specify what that requirement is in terms of behavior. Now, this is not meant to be a design, because we're not specifying how that happens. We are specifying what needs to happen. When I get this input, I'm expecting things to happen. Whether I'm doing that, digitally or analog, whether it's a diesel engine or excuse me, braking system. So whether I'm using analog brakes or disc pads or hydraulic braking, none of that matters. What are the required input-output control data transformations? That's what I'm specifying in terms of requirements. And that's what this specifies in a formal language. And the advantage of this is now I can look at this complex set of requirements and say, so what if the driver does this, and then this? Or what if this input comes and then that output goes? What happens in that case? Very hard to look at and answer those questions if all I have is a big textual specification. But very easy to evaluate if I have this computable, executable model. As a result of running this model, I can generate these sequence diagrams. These are different runs of that model under different circumstances with different inputs, in different orders, different timings, different input values. To see that, yes, in fact, in all these different cases, it does what I expect. Or if it doesn't, either the model is wrong or the requirement it represents needs to be fixed. A big question I get a lot of times is, so if I'm doing models in system engineering and I'm doing models in software, how do I kind of connect them? How do I connect these different processes? How do I connect system engineering with downstream engineering? And so I think the right answer is a model-based handoff. And because as we go to the trouble to create engineering data which is complete, accurate, consistent, and correct, we don't want to lose that information now to going to text and to this ambiguous language and then try to do something again precise. We want to do a model-based handoff to conserve that engineering fidelity. So if we go from a system engineering model down to our downstream engineering model, which includes software, electronics, mechanical, and so on, we have to somehow define, so how do we get there from here, right? The miracle occurs, right? How do we get there? What is the nature of this miracle we're talking about? So in the harmony process, we've got this kind of workflow. I don't have time to go into complete detail. We talk about maybe doing a separate webcast on that if there's interest. But most of the system engineering model deals with what we call logical specifications, logical data. What are the logical necessities of this information? For example, if I'm going to send a message off to a radar, look in this sector for things in my airspace. So I might model that as an event. Go to this sector. And then I want to talk about, well, what does it mean to look at the information for a trackback? Well, okay, I've got a range, and I've got a combat ID, and I've got velocity and altitude, and I've got position, and I've got these various set of properties. So how accurately do you need to know that? How quickly do I need to know that? I want to specify the logical information. When I actually get to building the thing, it's not going to necessarily be an event. It might be a 1553 bus message with a particular command value, a particular data packet that it sends, a particular sector number, whether it's a particular range of values with a CRC on it. That's the physical interface. That is the representation of this logical interface. So as we do this handoff, we have to convert from this kind of logical notion to a physical realizable notion. So the subsystem teams can actually build the actual real thing. So that's what we do on this left-hand side, is we convert this logical data to physical data in terms of the interfaces, data, and flow schemas. And then on the right-hand side, we then need to allocate the requirements to the subsystems and to the engineering disciplines within those subsystems. So what are those requirements allocated are? Software, which are mechanical, or which have to be decomposed into more precise requirements so that those can be allocated to software, mechanical, electronics. And what do the interfaces between those engineering disciplines look like? Is it port mapped? Is it memory mapped? What's the port value? What is the range? All those sorts of details need to be worked out so that we can take this logical data and proceed to build a physical system. And we do that in models. Subset your modeling language. So if anyone here has read the UML or SysML standards, they're pretty complex. The UML current standards are 1,050 pages split across 3 different specifications called superstructure, infrastructure, and XMI. And the SysML takes about 80% of that and then adds another 250 pages. Right? So I'm one of the authors of both the UML standard and SysML standard. And it is complex. In fact, we call it the hairy underbelly of the UML. Pretty complex stuff. So how do you address that? Well, the first thing I'd have to say is, oh my God, get some training. Yes, you're smart enough to figure it out on your own from the specification. Absolutely. Like, I expect that everyone on this phone call go learn all about how to solve hyperbolic partial differential equations. I'm sure you can do that. Get a book on it, start reading it, start doing exercises, and in some period of time, 6-8 months, you'll be an expert. You know how to do that. That's not perhaps the most efficient way to do that. That's why colleges teach classes, right? So that you can have people who are experts help you through that learning process. So my first response is, oh my God, get some training. Yeah, you're smart enough to do it on your own, but why would you want to? Secondly, the way you deal with complex languages is you subset them into simple languages, the parts you need, right? So the idea of minimal SysML, I wrote it as a profile of SysML, and it has a minimum amount of stuff. So it's about, something like 25-30% of SysML. But you can do most of the stuff. So SysML, for example, has full ports and flow ports and standard ports and proxy ports. We only nearly need one, proxy ports, right? The other have some value, right? I'm not saying you'll never ever need them, but rarely will you need to go beyond just proxy port. And rather than have interfaces, interface blocks, we'll just have interface blocks because they work with proxy ports. So we simplify it by taking stuff out that you're unlikely to need. And if you come to a need later on in time, you can add those incrementally as you need them. So the idea is that you're going to address the complexity of the language by removing the parts of the language that are little used. Right? So along with that, in the Rhapsody tool, we've developed a set of perspectives. So I and Grant Bleakley and a few other people got together to decide what should these perspectives be. So if you look at this, you see the novice in the upper left-hand corner. For a block definition diagram, we see a few tools over on the diagram toolbar. And so this is a novice, somebody who's maybe not an expert. These are the things you need to do, almost all of what you need to do, right, with respect to what block definition diagrams are good at. However, we have different perspectives that add in different features in the language, depending upon a combination of what your worker role is, whether you're doing requirements or you're an architect, you're doing trade studies, or you have an advanced user. And we offer different tools depending upon that need and that basic ability. So you take the advanced, for example, same BBD diagram, you've now got all the tools available. And there's a bunch of tools you can put on block definition diagrams. So we have this set of different perspectives, and these are the ones that I and Graham and other people came up with, where we have intermediate requirements engineer, intermediate architect, intermediate trade analyst, advanced, or just kind of basic novice kind of perspective. And you can actually take reps and you can add your own perspectives. If you have a particular role or level that you think makes sense in your organization, you can modify this to present certain parts of the language. And so we simplify the menu structure, the kinds of elements you see in the language, depending upon this perspective. And you can change perspectives dynamically as you work on a model. So you can take the same model and say, oh, I need to add this other feature, go from basic to intermediate architect, and now you have more features available. You can add those elements in your diagram. Design patterns. So design is really selection of a solution that optimizes a set of properties of your system. So what we call the functional model is typically specifying what we need to be fundamentally correct. And then during design, we not only want to be correct, that is, we want to comply with that functional model, we also want to be optimal against some set of what are called design criteria or measures of effectiveness, MOEs. Design patterns are different solutions that give us different weighting factors of these different MOEs, these different design criteria. So we select the best solution for our particular problem. So design patterns, essentially we use existing solutions that have been proven effective, that have certain benefits and costs, so we can make our best choice. So first of all, design patterns are generalized solutions to commonly occurring problems. So we look at a number of solutions. We can abstract or use the same kind of approach. We can abstract away the solution by taking away the problem, platform-specific characteristics, and deal with what's necessary logically to address the problem. So now we can apply it to a new novel circumstance, a new novel platform, to solve a similar problem on that new platform, right? So they're generalized solutions to problems that occur commonly. Now, if you Google design patterns, last time I did this, I think I got 4 million hits. So there's a lot of solutions out there that people have worked on, but they have different cost-benefit ratios, different things that are good or bad about them. And they allow us to leverage others' design expertise. We don't have to reinvent everything all the time. Now, all design patterns optimize certain properties at the expense of other properties. That's what optimization does. So we can pick a best fit. And you can apply this at different levels of architecture, such as architectural level design, collaboration level. We've talked about collaboration of elements, realizing perhaps a use case or user story, or detailed design, individual algorithms, functions, classes, data structures, right? And of course, there are books written about this. I've written a couple myself, but there are other books as well on these patterns that allow us to address the kinds of problems we need to solve in building our systems. So this is just a quick example of what that might look like. We've got this analysis model where we've got a train going down the track. And we've got wheels that spin, and they've got hash marks on them. We have a laser that shines a light and a receiver, so we can look at the reflectance. And as the wheel spins, the reflectance changes because of these hash marks on the wheel. Given that we know the size of the wheel, we can compute the rate, and from that we can deduce how fast the train is going. Okay? And then we come up with train speed. And then we might have a number of different clients for train speed. So maybe in every car, we've got a display. As the client train speed, it shows how fast the train is going. And we might have 4 or 5 engines, and they are trying to do loop control the speed of the train. Right? So how much output they get, they're trying to maintain a constant speed, so they put out more output depending upon how effective it is in terms of moving the train. Right? So we've got speed controllers. So now we have a couple of problems we want to optimize. For example, all these are connected, all these cars are now connected across a bus. And we would like to minimize bus bandwidth. So if I've got all these things, one thing I could have is I could have all these elements. They know how to talk to train speed, so they ask train speed, so what's the current train speed? Now they don't know the conditions when they're changing or when they're not, so they have to ask at the fastest rate they would ever need the information. So maybe let's say 10 times a second. But it might be going through Kansas. So for hours, they're going exactly the same speed. They're wasting bus bandwidth. Okay? Also, we go into the station, we might add some cars, take some cars off. We need to be able to dynamically add and remove these. So how do I do that? Well, we look in the literature and we discover that there's a pattern that solves this problem. It's called the observer, also known as publish-subscribe pattern, where we've got this element called the abstract subject. And it knows information of interest. And it has operations, methods, like subscribe and unsubscribe. So an interested observer can subscribe the information, and it gets added to a notification handle list, which has the address of how do I talk back to that observer. An IP address, function pointer, whatever the technique is. Okay? And so observers can come and go, and now the subject can now decide when it's appropriate to update that information. So for example, when the data changes, right, or every so often, it can decide what's appropriate for pressing the data off. So it solves both of our problems. And then we do what's called instantiation of the pattern. We have elements from our model that are unaffected, elements from the pattern, which are these glue objects that connect the pattern up to make the pattern work. And then there are these formal parameters. Those are the places where we substitute our elements, some of our elements from our design, into these roles inside the pattern when we instantiate the pattern. And now we have a design model. We move from an analysis model now to a design model that optimizes some properties of our system. And that's basically how you use design patterns. Okay, number 3, connect work products with traceability links. So as engineers, we create many different work products. Requirements and architectures and designs and test cases and safety analyses and reliability analyses and test plans and all these different kinds of work products. It's kind of like Goldilocks and the Three Bears. If we separately interview Baby Bear or Mama Bear or Goldilocks or Daddy Bear or Papa Bear, we get different stories. But they're all really the same story. And how do we demonstrate that it's the same story? So we have all these different work products that are done in different tools, use different languages, like FTA diagrams for safety analysis, or FMEA for reliability analysis, or control models for control models, or textual for requirements, or use cases for this, or block diagrams for design, or test cases for how we're going to test it. How do we demonstrate that these are really all the same story? They're all connected. That's where traceability comes in. So we would like to be able to ensure the requirements are met. We'll be able to ensure that all requirements are verified. We want to be able to lower project risk, create an audit trail to make sure we followed our process, important for safety critical systems. We want to ensure consistency among the work products, consistency of information, and coherence of information, and we want to be able to maintain that. So we build up our traceability model. So here, for example, we've got requirements versus implementation or design. So here we've got a requirement for which there are no design elements. Well, we've got an unimplemented requirement. Or we've got a design element for which there are no requirements. Why did we do this? There are no requirements for that. It's just an annoyance for most systems, but for safety critical systems, it means you can't verify the system against the safety objectives, right? Every design element in your design for a safety critical system needs to be there to meet a requirement. Otherwise, why is it there? And it's not just requirements and design. There's also testing and reviews and test results and safety analysis and security analysis. There's a whole bunch of things you need to show that are related. And so in this kind of trace meta matrix, think about these various work products we create. Stakeholder and system requirements, subsystem requirements, dependability analyses, safety, reliability, security analyses, architecture control models, detailed design, test cases, test results, QA records. How do these all relate to each other, right? So these are, in a typical system, these are what you would expect to see. Now these are showing the relationship between work products, but traceability is actually done at the statement level, not document level. So the system shall do this, needs to relate to a specific test that demonstrates it does that, to particular parts of the design to implement that, right? To a particular part of the safety analysis that talks about is that safe enough? To a part of the reliability analysis that talks about is it reliable enough, okay? So it has to done, the traceability is done at the statement level. So although you can look at this on the, when you download the presentation, the R's basically stand for, it's just required for any good repeatable process, right? The O's are optional, and the S's are required for safety critical system, right? So these are typically the kind of relationships you see, and the reason why the bottom diagonal is blocked out is because it's symmetric. So really you only need to worry about one half of the matrix, because the other half is just a reflection of it. So how do I do requirements traceability and design traceability and test traceability? There's a few ways. The way I primarily kind of like to work myself is I typically work in the graphical views and draw these trace links on the diagram, and then I summarize them in matrices and tables. However, you can also work directly in the matrices and tables if you want to do that, right? So I can, in this case, what I've done is I've drawn the diagrams and I've added in the trace link to requirements, those are the yellow boxes, and then I've summarized that in the matrix down below. That's a reasonable way to work. You can also work directly in the matrix. So here we've got a requirements versus use case allocation kind of a matrix, and I can work in the matrix and double click on these cells to add the relationship. So I can work that way if I want to as well. I can go to third-party tools to do this, like Doors or Realm to do that as well. So there's a variety of ways that I can actually make that work. Rhapsody also has the ability to create your own kind of custom multi-level traceability views. So for example, I can go from blocks to attributes to use cases to requirements to test cases and so on. I can add the views depending upon what views I think would be useful, what questions I'm trying to answer in terms of my traceability. And in Realm is a particularly interesting tool because it allows me to work in not just the model, but all kinds of additional tools like RTC and RQM for RTC for project management, and for tell us where you've had your breakdown tasks and your task lists, and then you might have requirements done indoors, you might have your design in Rhapsody, you might have test cases in RQM. And not just UML tools, but also IBM tools and non-IBM tools. And this can build this arbitrarily expandable graph, depending on how deeply you want to decompose, how deeply you want to go down that rabbit hole. Okay, number 2. It is better to avoid defects than to fix defects. So the idea here is that what you want to avoid is, putting all the stuff together, create this steaming pile of your system, only then to discover perhaps there are defects in it. It is much easier to build systems that are constructed of demonstrably correct pieces and then ensure that it works as a system than to put it all together with pieces of unknown quality and then try to beat it with a testing stick until you're done, okay? Which is a problem we see in a lot of systems. So I have this idea that if I want to integrate an automobile or an aircraft, I can do it in a day. Okay, I'll give you a week. I'll give you a couple of weeks. It shouldn't take a year. It shouldn't take 8 months, okay? It should be easy because all the pieces have no defects in them, and I'm just putting it there to the final assembly, make sure that it all works. It should be an affirmation of correctness, not at the time at which I begin to find problems. Because then I've got this huge delays, huge cost to identify and fix the problems. So a lot of people's plans look like this. We've got a planned final operating condition, the target, and then we're gonna party down. Reality is something different. And I've seen companies do this time and time again on the same project. We've planned, 12 months. It consistently takes us 14 months to get the IOC, initial operating condition, and then another 6 months to get the final operating condition. And yet they still plan on a year. Right? It's crazy. So the time the initial operating condition is already late, and it's not ready. There was requirements churn, tests fail. We built the wrong product. It didn't meet the customer need, for example. So then we have this product stabilization period. I worked with a German company a few years ago where they consistently did this process where they had around 12 months, and they had another 6 months for stabilization. So I said, let me get this straight. You spend 12 months putting defects into the system, and you spend 6 months taking them out. Wouldn't it be better to take some smaller number, say 14 months, and just have no defects in it at all in the first place? And they had to admit that, yes, that was probably a good idea, and in fact, we worked to achieve that. And we did actually achieve it. Because when you do this product stabilization, which is code word for, yeah, we're trying to fix all the stuff we did wrong, sometimes the outcomes are not what you expect or want. Okay? Question is, how do we do that? How do we avoid defects? Well, I like to think of doing this at 3 different time scales, what I call nanocycle, microcycle, and macrocycle. Nanocycle is a small cycle, hour or less. So as I'm doing a work product, you think of code, you think of your architecture, but it could be any work product. It could be your safety analysis, it could be your requirements, it can be your architecture, it could be your test case, whatever work product you're creating. I do a little bit and I verify that what I've done so far is right before I move on. And this is 30 minutes, 20 minutes, an hour, some small period of time frame. We call that the nanocycle. We also do this at the iteration level, which is typically anywhere from a week to a month. It could be 6 weeks, but it's that kind of time frame. Where we bring multiple engineers' works together and integrate it and demonstrate that, yes, that all works together at this larger time frame, this microcycle, would have roughly kind of month-long kind of time frame. And then we also have this kind of project scope, we call the macrocycle, where we have waypoint like customer release, customer final release, or beta release, or some kind of milestone kind of marks, CDR, PDR, SSDR, those sorts of kind of milestones, if you're familiar with those. So nanocycle level, this is kind of works. This is for software development. This is what we call high fidelity modeling, where we model a little bit. At the same time, we generate test cases for how we would demonstrate that that piece of the model, a couple of classes, part of a state machine, something like that, is correct. We then refine the collaboration. We translate. I don't care if you do push a button in Rhapsody, you generate the code, or you bring up Emacs, you pound it out. I don't really care. And we fix those defects, identify and fix defects, and we do the next bit. And this time frame is less than an hour. Okay, small period of time frame, continuously making sure that it's correct, right? At the iteration level, we do the same thing. So this is an iteration for, this is again in the software process. It also applies to the system engineering process. But in the software process, we do an iteration. So we've got perhaps 35 use cases, let's say. And each one of these is average 45 requirements, let's say. So a given iteration, which might take a month long, we're going to do, this iteration we do 2 use cases, the next iteration we do 3 use cases, and so on. And we're going to walk through this. We do the high fidelity modeling. We just saw that before. We do continuous integration, all the time integrating on a daily basis perhaps. The engineers work together to make sure it all fits together. And at the end of the iteration, we verify the system against those set of requirements that we've implemented so far. So in the first iteration, you've got perhaps 2 of the 45 use cases done, and we verify that, yeah, that much is done, and is correct, and is demonstrably so. And we may even explore that with the customer, allow them to validate, yes, this part meets our needs in this way. Or you come back and say, nah, that's really not what we wanted. That's what validation is all about, right? So we do this again incrementally, and this is at the microcycle level. Okay, number 1, continuous verification. So the idea goes along with number 2. The idea of this is that the best way not to have defects is you continuously verify. So the way that I think about it is kind of like brushing your teeth. Suppose you decide that tooth quality is really important to you. So on December 31st of every year, you sit down and you brush your teeth for 4 hours. Because by God, you're going to brush quality into those teeth. What you discover pretty soon is that there's a high maintenance cost associated with doing tooth quality in that way, right? A lot of doctor visits, a lot of tooth extractions, a high cost, right? A better way, an alternative way, is to brush your teeth once or twice a day. every day and maintain the quality of your teeth all the way through. Systems and software development is like that. Okay? So the best way to have high quality at the end is to continuously verify what you're doing all the way through. Okay? And this is true not for just source code, not for just object code, not for just requirements, but there are so many different work products we create. Stakeholder and system requirements, subsystem requirements, safety requirements, security requirements, trade studies, system architecture, software architecture, electronic architecture, concurrency architecture, discrete behavior, continuous behavior, system design, control models, physical and logical data schemas, trace metric, test specification, test plans. We create many, many different work products. So when I talk about verifying that the system is correct and the work product is correct, I'm not just talking about the final system or just not source code, but all of our work products. We need to be able to somehow verify the work product as we are creating it is in fact complete, consistent, accurate, and correct. So let's take the example of requirements. So requirements are correct if and only if they correctly represent the input-output control and data transformations and their properties, such as performance and safety and reliability and so on, right? So we have some sort of inputs, they come in certain orders and sequences and time frames, certain values that produce some specific outputs, right? And for requirements, we don't care what kind of hamsters you have in those hamster wheels. We only really care about what the transformations are, right? Not sure why, but my computer is now locked up. Well, there it goes. Yay. Our hamster was
Bruce,
just tired.
the animation is working, and it's moving forward. This
okay,
requirements don't specify.
Yeah,
okay.
So all better now. I guess the hamster was hungry. Okay, so requirements don't specify the hamster. They specify what the hamster has to accomplish, but not how the hamster goes about it. So how do I verify my requirements? I don't want to do this at the end of the project after I built the aircraft and say, whoops, what do you mean you didn't want propellers, right? Well, I have to verify my requirements are good. There are three fundamental means: review, test, and analysis. So reviews. So reviews or inspections are the weakest form of verification, but they do add value. They're not bad things. I recommend them. So when we talk about these three methods, these are not ands, this is not ors, this or this. These are ands, this and this. Okay, I recommend all three. Okay. So inspections add value. They allow you to ensure that you're meeting company standards. Maybe you have a standard that says, this is how we're going to use MBSE for our coding standard. Fine. Well, for MBSE, there are some tools that allow you to do it, but you know, did you follow the naming convention, for example? A little harder to verify. For modeling, you maybe have some modeling standards, how models should be put together, how they should be organized. So the Harmony process has a whole set of these, model organizational standards, for example. How do you ensure that? Well, QA does that. That's what QA does. We call that syntactic correctness, okay? Syntactic verification. It also allows subject matter experts, architects, peers to identify issues with the work products, and allows you for verification of informally specified work products that are not easily tested or formally verified. Some issues. Very easy to miss subtle problems because of the complexity of holding all the information in your head when you walk through it. It's highly dependent upon the skill and attentiveness of reviewers. And there's a huge problem with vigilance. So you look at like a big aircraft, you might have 200,000 requirements for something like a 727, right? Something of that scope. So if you're going to sit there and review those requirements, that's a hard problem. Pretty good for the first 30 minutes. But by the second day, you probably no longer care and you're longing for death to get out of the room, right? By the second month, you've got your resume out there, you're looking for other solutions to your work employment problem, right? So that's a problem. So there are ways you can address it to some degree, but that's a fundamental hard problem with reviews. Now, they can also be very expensive and lengthy if you don't manage them well. So the Harmony process has reviews and inspections based on Fagan inspections. We have to have a link here for Fagan inspections. So they use inspections in a certain specific way to maximize their utility. But they can be very expensive. They're not well managed. So that's a known problem with reviews. Another way is by testing. So if you look at models, talk about computational models. There's a subset of those models called executable, which are where execution has where the computation has a direction. Okay. For example, I've got P equals NVT, right, for pressure, volume, temperature, and in a gas system, right. I can start with pressure and determine and pressure and volume determine temperature. I can start with temperature and volume determine pressure. I can do this in any direction. An executable model is where I have a particular direction. Okay, so it's a directional computational model, if you will. And so I can test this by giving a known set of inputs, certain timing, phasing, sequence, and values with a known expected set of outputs. So it's pretty easy to do testing, and I can get arbitrarily good coverage. But meaning that I can get better coverage by adding more test cases at additional cost and effort. Okay? The cons are testing can be very expensive. 60% of the cost of developing embedded systems, on average, is in testing. So it can be pretty expensive. Higher level of coverage, it's non-linear. So as you get to more and more increasing levels of coverage, testing gets harder and harder and more expensive. And you can, in principle, never be exhaustive because there's an essentially infinite set of possible input sequences, orders, timings, and values. So you can get arbitrarily good, but you never be complete. And the last method is what we call formal analysis. Formal analysis applies mathematics to quantifiable properties of a system to demonstrate certain properties. Pros are you can get complete coverage. Okay, and it's available at different levels of rigor. Let's say, for example, you have a state machine using lightweight analysis. You can determine have I covered all transition paths on my state machine, right? Coverage analysis. It's a lightweight form of formal methods, right? So all the way up to theorem proving. For example, I've got an elevator, and I want to be able to demonstrate that I can, if all elevators are currently unoccupied, I can guarantee I can meet a service request within 2 minutes. Okay, I can always meet that, right? So I can do theorem proving as well. Cons are typically expensive, very hard to do. Typically, you have to have a PhD in formal methods to really be good at applying the formal methods. Very, very hard. A project I worked on, for example, for NASA, it was limited to a very small set of the problem space, 2 or 3% of the project I worked on, because it's just so hard to do, right? And also, something that's not often admitted, that there's some assumptions you make. For example, talk about the elevator example, that the doors don't break, that the motors don't fail, right? Those are invariants you're assuming are true. And if you violate those invariants, you can say nothing about the validity of your conclusions, right? So that's why I really think that you need to have all three of these methods to address the verification of your work products. Okay? So here's an example in Rhapsody of a computable model where we've got these 3 different state machines executing. This is a GIF that I made ahead of time. But the color coding shows currently and last active state of transition, and the sequence diagram is drawn dynamically as the elements in this model interact during the course of this execution test case. So I can actually visualize that. I can set breakpoints. I can put in different test cases. I can instrument the testing. And it's a way to visualize, is this work product correct? And this can apply to requirements or for design or for implementation or architecture, a variety of different kinds of work products. So we're kind of at the top of the hour. So in summary, really you should model, create the views of your model to answer specific questions, right? Understand that all models are abstractions, so you need to be focused and clearly identify what the scope and purpose of your model is, so you can write the and include the information relevant to the questions you want to ask. You need precise results, precise models, to answer the questions because imprecise models don't really do a very good job. Requirements models allow you to identify defects, particularly expensive defects or requirements, early. A model-based handoff preserves engineering fidelity, resulting in better outcomes of the system. Because SysML, UML are complex, you can subset those languages using perspectives or minimal SysML or minimal UML profiles to subset your language. Design patterns is a wide, huge literature base for design solutions to various kinds of problems. Traceability links are hugely important so that you can demonstrate the consistency of a wide variety of work products. It's better to avoid defects by applying agile methods and early practices like continuous integration and test-based development to avoid defects. And key for all your work products, not just your code or just your design, is continuous verification of your work products. That's the way you ensure quality. If you want to know more, I've written a bit on these topics. And with that, I'll release control back to Mark so we can answer any questions you might have.
Thanks, Bruce. Excellent presentation. So for the attendees, if you would like to ask a question, just go to the question plus mark on your GoToWebinar control panel, and you can go ahead and submit a question to me, and I'll read it to Bruce. I'll read the questions in chronological order as questions roll in. I will reply to everybody, let you know that your question is coming up next so that you can pay attention to Bruce's answer. So Bruce, the first question is, do you have best practices regarding collaboration? How to collaborate and hand off models in multiple team environments, how to integrate work products from teams in a model on a higher level, and how to structure. So can you comment about that a little bit?
Yes, those are like 4 questions, and they're all around the same kind of thing. Ultimately, those are process questions. And so yes, the harmony process for system engineering is described in the Agile System Engineering book, and for embedded software is described in the Real-Time Agility book. Those questions are addressed because those are ultimately process questions. How do we collaborate? How do we work? Those are ultimately and at the core process questions. How do I do this? What do I do? When do I create it? How do I organize it? So for model organization, we definitely have recommendations on the best way to organize models to facilitate both engineering work and progressing to the next steps in the process. So we definitely have some strong opinions about that. If you either Google me with those questions, you'll come up with some papers I've written, or these books have articles on it, or I think that in some previous webinars we've touched on those topics.
Okay, great. Let's see here. Next question, Bruce, is I think you were working on a security profile for UML and SysML. Have you released that work yet? There's
2 ways to get this work file. You can send me an email. There's both an FTA profile, fault tree analysis profile for safety analysis, and a security analysis profile for UML and SysML. You can send an email and get it. You can also go to a place called Merlin's Cave, which is run by another IBMer called named Andy Lappin. So the Merlin's Cave, and on there are these profiles available for download from his website. So Merlin's Cave, Rhapsody should get you to the site, and then on there you can look around and poke around and find them. So yeah, they're available. We're looking into making them a standard. There's some work in the OMG to standardizing them. Right now they're available for Rhapsody and free to use.
The question and answer panel is open. Attendees, feel free to ask a question. I can read it immediately. So Bruce, it looks like that's going to be it for the questions. Anything you'd like to say before we conclude the webinar?
Well, I hope these have been helpful and perhaps thought-provoking. I'm a big proponent of modeling because I think, well, one, model is fundamental to how we think about things, and it also allows us to explicitly come up with systems that meet all of our needs, both in terms of functional and optimization requirements. So I think it's just really the best way in which to work, and applying models in the best way takes experience, it takes practice, and it takes thought. So good luck in your modeling efforts.
Thank you, Bruce. So for the attendees that are still on, if you'd like the presentation, which has valuable information on the last page, including the books that Bruce has published, feel free to download that in the handout section of the GoToWebinar control panel. If you have any difficulty with that or you don't have time to do it when we conclude the webinar, feel free to reply to my automated email that I sent to all registrants, or you can reach out to me directly. I've copied and pasted my email address in the chat window there. So with that said, and thanks again, Bruce, I really appreciate that presentation. So with that said, we're going to conclude, and everyone have a great rest of the week. We look forward to having you return on future Enlightenment Series webinars, and with that said, the webinar has now ended. Take care all.